Here we are having fun. We're doing hardness tests again, except this time we're doing it on AUPD wire. Melted it last night and it turned into AUPD. Very nice stuff. Okay, here's how you check hardness on things. We check the relative hardness of a metal or a mineral or an amorphous substance like glass. And glass is a known quantity. It's 5.5 on the Mohs scale of hardness, exactly like stainless steel. This is just regular old steel. This is not stainless. It's, attracted to a magnet real well and that sort of thing. So it's just plain old steel. It's about 5 on the Mohs scale of hardness. Aluminum is about 4 as a general rule. Copper is about 3. Gold, pure 24 karat gold, is 2.5. Same as our fingernail. So I can't scratch gold with my fingernail. But if I had teeth, I could bite it and leave an impression in it. Okay, I could, boom, leave an impression. Okay, but if I try to scratch glass here, my wire does not scratch the glass. Right? If it's aluminum, it shouldn't scratch the steel, even if it's sharp, right? If it's sharp, doesn't scratch the glass. It's harder than steel. This is not something you can fake, right? Not something you can fake. And I'm not honking on it or anything. I'm just dragging it across the surface with my finger on it, about like you draw with a pencil. See? And it just scratches the surface because this is harder than this. This doesn't scratch the surface, right? We know that. You know that the wood's not going to scratch the surface. It's a relative hardness. I can turn around and use this steel on this piece of bamboo, and bamboo's the hardest wood in the world, except for ironwood, which grows here in the Sierra Estrella, where I live. And this is about 2.5 on the Mohs scale of hardness. We can't scratch it with our fingernails, and it doesn't scratch our fingernails either, right? It just slides off of them, and that's what happens when they're the same hardness, like this. This is about 5.5, about the same as stainless steel. And it's actually just a bit beyond, because I can scratch stainless steel. This does not respond to a magnet because it's stainless steel. A little bit, just a little bit. But they use stainless because it's getting hot all the time, and under a great deal of mm, there's a lot of hot and cold and hot and cold and hot and cold, and the stainless is more able to deal with that than regular steel, for instance. The heating and contracting of steel wears it out. Part of what wears it out, and it starts to oxidize more quickly, and it goes away. This is palladium. It doesn't do that. It doesn't get hot, for one thing. Really hard to make it hot. Um, I can't melt this anymore with my torch. I was holding it um, with a pair of pliers, just in case. And I heated it along its entire length for some minutes, and then concentrated on the end, and I could not melt it with not just with my cigarette lighter thing here, like this guy. All right, that gets a pretty good flame. This is a serious little torch. I can't melt it with that. I couldn't even touch it with that. And I've got a culinary torch here that I've been using that has got a real flame for a real torch, and I can do real work with this. I can go, do plumbing or solder silver or whatever with this torch, and it's a very handy little device. And it is capable of melting aluminum in, a couple of seconds, a few seconds. You heat it up, maybe 10 seconds on a piece of 3 millimeter aluminum wire, like this. Like this. Now, this is attached to this whole roll, and that acts like a heat sink, right? And so you might need to heat it a little longer on something like that. But if I lop off a small piece of that, and it's just aluminum, right? Let's see the difference here. If there is any difference, is there? Let's get closer. This is the new aluminum. Hasn't been heated. And it's pretty much just silver colored. Here's what it looks like when you heat it. Not silver colored so much anymore, kind of the goldy colored. That's kind of pretty, I think, huh? Yeah, I think that's beautiful, man. So you know what I'm using this for? I'm using it to clean my pipe with. Far out, huh? It's it's a piece of this stuff that I converted. So, gee, you know, So the interesting thing about this conversion is that it loses weight. my uh, my 4 grams of aluminum wire yesterday. No, it's now 4 grams of AUPD wire started out as 4.9 grams of aluminum. How about that? Don't ask me how. I don't know. I don't know. But it's actually more flexible. I can bend it pretty easy with just my finger. This is a little bit more difficult. And what'll happen if I bend this repeatedly for a minute or so, I can break it right where I'm bending it. It'll just break. This one will deform and reform back to its original shape repeatedly for a long, 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 long time because it's so very dense. It doesn't oxidize, even with high voltage electronics. That's what these are used for. Um, Things like the anodes of spark plugs. Boom. Doesn't oxidize, doesn't transfer any metal. When you use copper, for instance, if you ever change spark plugs in a car, the old-fashioned ones with the steel or whatever it was on the spark plug part, and then they'd have the copper anode up the middle. Um, you had to replace them every, few thousand miles, 3,000, 6,000 miles in my old VW, because the spark built up crap on the ground side because there was metal transfer from the anode to the cathode. Um, and that's like how arc welding is too, right? These don't actually, the spark plug doesn't actually touch, doesn't have to. The transfer is going with the flow of electrons passing from the anode to the cathode. And these don't do that. This doesn't do that. And it doesn't oxidize and it doesn't wear out. So you can have a spark plug that would, pretty much last forever because you don't have to make the other side out of steel, right? You can make it out of this stuff. Actually, you make it out of aluminum first, and then make it into this stuff, right? We've got all these old dead beer cans and stuff that we can turn into AUPD with a little heat. Far out, man. I mean, it is tremendously far out because I have like zero infrastructure here, and I'm creating palladium wire from the dust on the road. Somebody was so unimpressed with the dust from Georgia that I'm using. They sent me a 5-gallon bucket full of it, gratis, free, 10 years ago. And that's what made this. That's where this metal came from. This is no longer aluminum. There's no aluminum left. I boiled it off. It exactly replaced the aluminum with a high melting point AUPD. Melts at 1550. But the gold in there melts a little bit less, right? Like about 1050. And so when you get it up to the temperature of palladium, where palladium begins to melt, um, the gold moves through the palladium towards the heat. Right? Palladium has a cubic structure, little cubes of metal atoms, ions, because they share electrons, right? They share electrons with each other, but not as a covalent bond where they're sharing both ways. It's just a one-way thing. So this atom can share its electron with the atom next door in that direction or in that direction. And most of these metals only have one electron in that outer valence orbit, so there's not like a lot of variation on that particular one. Um, and even this is platinum and palladium are, by row 13, column 13, I think. Um, anyway, and the same one with nickel. Nickel's the first one. Nickel's right next door to iron, and it's in the lowest row of the transition metals in the periodic table. And nickel, and then palladium, and then platinum are the primary platinum group metals. Things like iridium and that sort of stuff are next door in the other columns. Columns are based on the configuration of the nucleus and the protons and neutrons that make up the nucleus of the atom, and they have certain configurations that give stability for the number of protons and neutrons present. Um, mm, Platinum and palladium have a single electron in their outer valence orbit. Nickel, too, I guess. Necessarily so because it's in the same column. So I can extrapolate, even though I haven't read anything about nickel other than that it's next door to iron, and I just, what the thing is when you're an autodidact like I am, is I only study what I'm interested in, man. I wasn't like trying to get a better job and passing tests. I was just reading for fun. And I went out and started looking for things, and that reading has been serious business about finding out how this stuff works, how things form in nature. And this is the result of 35 years of pretty serious research. I did other things. I worked at other jobs to pay for my science habit because I didn't get any funding from outside sources. I was just trying to satisfy my own curiosity. That's what education is. It's not something someone else does to us. It is indeed what we do to satisfy our own curiosity. Mine's like this flame, and it just burns brightly every day, and I have to stop and look at the world with my camera. Cameras measure the universe with light. Peace, y'all.